Okay, today we are going to talk about an ordering phenomenon which we have not addressed so far. So far, we have been interested in homogeneous phases of flexible chains mainly. So we had the temperature here versus concentration of the polymer. And then we were at high temperature, we were talking about this homogeneous phase, like we heard from the question, screening of extra volume interaction, etc. Then when we lowered the temperature, we had phase transitions like that. And then here we had spinol decomposition, nucleation growth, etc., etc. This is for UCSC system. So that's your TC, meaning critical temperature. This is critical temperature. Now today what we're going to talk about is a melt. Now here is a melt. And again, we talked about the high temperature phase before, high temperature phase in the melt as a function of molecular weight. Then we had Rouse to entangled behavior at high temperature. Now what happens now is if I lower the temperature, you take the melt and lower the temperature, then there you hit one temperature, right, depending upon your particular chemistry, right, and below which it'll make crystalline phase. I'm going to put it in inverted commas because we're going to talk about what that is going to be. And above that is melt. So here is a melt at above, although this is, when I say melt, this is volume fraction is equal to 1, right? That's what I mean, no solvent. Right? So above this temperature, which I'm going to call this to be TM0, there is an equilibrium melting temperature, right, above which it's a liquid, and below which it's a solid. Even the liquid is a solid, as you know, right? It looks like a solid. It's a viscoelastic. But below this temperature, you have what's called crystalline phase. So this is a first order phase transition, okay, from the liquid to a solid. That's what we are going to talk about for this lecture and probably for the rest of this course. Right. So how do we do this? Let's go to a simple case. Suppose I have free energy of, suppose I have a small molecular liquid, right? Small molecular. Before we talk about polymers, let's talk about small molecular liquid. So I'm going to write the small molecular liquid as something like this, randomly placed like that. It's a liquid phase. Then what I do is I take this and reduce the temperature. I decrease the temperature. Then what you'll know, as you know already, what will happen is these would be organizing in a regular array. I'm writing a square array, but depending upon the nature of this is a crystal, ordered, let's say crystal, and this is a disordered liquid. So how do we discuss this? Suppose I take a plot of free energy. This is free energy of the system. In this particular case, I'm writing Helmholtz free energy, doesn't matter, at some pressure, fixed pressure. And if I plot as a function of the density, rho is the density. So this is an one component system. There are no mixtures. We have only one kind. Right? Then, corresponding to this particular situation, there's going to be a freezing point or melting point, right? So if the temperature is higher than the melting point, then as you know, liquid is more stable. And that means the density is low, right? The phase with the lower density is more stable. So the free energy landscape is going to be looking like this. That's a global free energy minimum. And there is a little bit of barrier. And then this would be the phase diagram, not a free energy profile, but T greater than Tm0. That's the equilibrium melting temperature, because in a free energy, I'm plotting like this as a function of density. The density being lower, this is lower than the local minimum. This is a local free energy minimum. This is a global free energy minimum. It is lower than this one. Therefore, liquid state is more stable. But then you reduce the temperature. For temperature equal to melting temperature, then the curve would look like this. This is a minimum, and again, this is also minimum. So this is degenerate. These two energies are the same. When the free energy of the solid phase, crystal phase, is same as the free energy of the liquid phase, and that's the place where you have equilibrium melting temperature. But again, if the temperature is lower than Tm, a low temperature, the global free energy minimum would be here. This will correspond to higher density. So it would be like that. So this is lowest point. That's a global free energy minimum, and this is a local minimum. So for temperatures below Tm0, you'll have the crystal phase as a most stable phase. This picture is universal. This is true for all situations, whether they are polymers or small molecules. So there are several messages that are portrayed by this figure. At any temperature, right, although, let's take the high temperature, although this is a global free energy minimum, that is, liquid phase is stable, it is possible to find some realization of the metastable crystal phase. Although thermodynamically the liquid phase, it is possible to realize there is a finite probability by which you can see a solid phase. And the probability by which I can see the solid phase is given by this barrier, right? This is a free energy barrier. This is global free energy minimum, and there is a barrier. If your environment such that the system can cross that barrier, by fluctuations, it'll go in here. So very close to the melting temperature, you will always have a globally stable state and some fluctuations into the other phase. It's possible. Right? But of course, if you take the temperature very high, somewhere here, then the barrier becomes so large that you will not get the metastable state. The probability that you are going to get the metastable state is going to be exponentially small, extremely small, right? Similarly, when I go to temperature below melting temperature, I can have the global free energy minimum state, but still there is a finite probability with which I can have the liquid phase. All right. This is true for small molecular case and also for large cases in principle. But the problem with polymers is what we have been talking about in the last lectures. Particularly, we are talking about melt and a high molecular weight, right? Above entanglement molecular weight, for example. Then the problem is how are they going to order? It's not going to be very easy, right? Because instead of this, suppose I had like more in a small molecular case. So I have like this. And then, as you know, right, there are several chains which are making up these monomers, like this. Now try to, just even as a simple exercise, try to make them into a crystal. So go back here. If I had unconnected monomers in the liquid form, when I lower the temperature, they'll all, because of the attractive interaction, van der Waals interaction between these molecules at lower temperature, they will get together and order. But that is not possible easily, right, for these things to order. So what will happen then is you will see something like this. This is a cartoon, right? So I have one chain. This is some sort of a nucleus. This will come like this, right? And then another chain will come like this, right? And this chain may participate in another nucleus, and then now the chains are different. Another chain may go like that, and then the third chain may come and participate like that, right? So while the monomers are trying to get together to make a nucleus of this type, or a crystal of this type, and now since they are all mixed up together, these units which are into the crystal will come from different chains. So if that happens, if I want to make a full crystal, it's going to be tough. It's going to be very difficult, because the only way this can become a full crystal is by bringing these monomers belonging to the same chain, which is participating here, to bring them all in here and then grow. So this strand, a tie chain, we call it tie. We call this to be, say, tie chain. For example, between this spot and this spot, that creates frustration, entropic frustration for the further growth. So what I would imagine is there is a birth of baby nuclei, small nuclei that will form in the polymer case in early stages, and then they'll take some time for them to course and some time for them to grow. Therefore, what I would expect, all of us would expect, is the following. Suppose I have, for small molecular case, I have free energy, right, as a function of free energy, as a function of, let's say, some order parameter, say density, if you like. So I'm going to write this to be some order parameter, which is a measure of ordering, right? So if you had small molecular cases, what you will see is a simple situation like, right? To begin with, there's a barrier, right? Remember, always there is a barrier. You know, you take your system in the high temperature phase, so the global free energy minimum is here, then suddenly I'm going to quench it. I'm going to lower the temperature. So suddenly it's going to go, it needs to go, it wants to go here. So between the initial state and the final state, there's going to be a barrier, which we're going to talk about later today, right? There's going to be a barrier. So in the beginning, there is going to be a barrier. Then it'll come down eventually to the fully ordered state. This is order parameters 1, completely ordered. So this is a pure crystal corresponding to this situation. Okay. So now for the polymer case, you cannot expect this because, yeah, in the beginning, yes, indeed, there is a barrier. It will go like this, something like that, and come down. But then there's going to be another barrier due to entropic considerations, right? I make this little baby nucleus, then they are going to be fighting with each other, and that's going to create a barrier. Then on and on, there's going to be barrier. Then they'll win, one of them will be absorbed, it keeps growing. So it's going to be complicated like this, some free energy landscape. And it's not clear whether I will ever be able to make the final state. And all evidences show that the global energy minimum is not at one, but at some finite state. If it's not at one, this state that emerges is semi-crystalline. We say semi-crystalline, right? It's a crystalline, but it's not completely, order parameter is not one under normal conditions. There are special situations, as we had during the question time, when you put flow, then you get rid of this entropy, all this entropy frustration, because they're more like a rod-like, stretched chain. Then they will make a crystal very easily. Similarly, even for polyethylene, if you put pressure, it's possible to make fully ordered state. But under ambient conditions, the entropy prevents the full ordering. And I hope you are able to appreciate why we invested so much time to talk about entropy, conformational entropy, because the polymer physics is completely controlled. The behavior of polymers, right, is completely controlled by conformational entropy. That's the one that distinguishes between polymer and small molecular case, between this phenomenon of crystallization versus this phenomenon of crystallization. Right? In principle, they will order when you lower the temperature, but in practice, there are problems due to conformational entropy. And this is really a wonderful thing, right? So when I say, why do I say it's a wonderful thing? So what we are saying is the free energy, right, is equal to E, energy minus temperature, right? And the biggest quantity is this entropy. In the case of small molecular situation, this is not that important, right? There is no conformational entropy. Therefore, the van der Waals interaction between these molecules dominate, control the melting temperature and how they order. So it's the energy driven. But on the other hand, when I have this problem, our problem of polymers, then this entropy makes a huge contribution to the free energy, as you can see from cartoon point of view, as you can see. Therefore, without taking into account this part, we are not going to make progress in understanding what we observed in polymer crystallization. And also, please notice that the temperature at realistic conditions is 400 degrees Kelvin, right? It's not very low. The temperature is very large. So since the product of temperature and entropy contribute to the free energy, and this is going to be extremely important quantity. And please notice, if you allow more and more entropy, right, then free energy is going to be lower, right, because of the negative sign here. That means the entropically frustrated situations become more promoted in this process. So we have to work with these entropic traps contributing to how these crystals grow. So this is the modern view, today's view about polymer crystallization. In all textbooks, what you will see is they will ignore this part, right? They will always think in terms of only energy. In all textbooks on most of the literature, but now we have made a revolution in addressing the contribution of entropy. Without this, we cannot go any further. Okay. Therefore, for all practical purposes, semi-crystalline state is the equilibrium state. If you want to have full crystals, fibers, for example, if you want to make a material with fibers or something like that, then you have to put a flow. Now, this is one of the strengths of your institution. Your institution is one of the leading institutions to understand the role of flow on polymer crystallization, unidirectional, bidirectional, etc., etc. Right? Right. But that's because you want to get rid of this. But if you have this, when you have semi-crystalline, what you have is it has very interesting properties because it could be more like a real crystalline solid. At the same time, it's highly elastic. So you'll be able to make materials going from hard solids or hard plastics versus elastomers. So that opens up tremendous opportunity to make all kinds of materials. In one extreme, suppose you have a plastic bag to carry your vegetables because you want to have some stretchability. At the same time, if you want to make a polymer, which is for aircraft, for example, right, or for a semiconductor device, encapsulating, packaging semiconductor device, and then you need hard material. So the how you play the strategic game of managing energy and entropy gives you tremendous flexibility to deal with polymeric materials. In fact, the fact that we have these two contributions in polymers made our modern civilization to be a polymer-based civilization, right? We had Stone Age, on and on. All right. Now brass the last century, maybe 2 centuries ago. But the reason why you see, when you look around in your room, you see almost everything to be made of polymers. And the reason is this beautiful equation, right? And the different terms are contributed by the various attributes of these polymers. Okay. So now let's look at facts. Okay, so this is what we think about it. We think about these issues even before we go to the laboratory and make measurements, or go to a computer and try to model. Just look at the general pictures. This is what we have. Now let's look at reality. I'm going to do this. I have given a handout. June Fine has it, and I'm sure she will distribute to you. Let me show the real world. What is amazing is, right? What is really amazing is this, right? You take polyethylene in a solvent like xylene, para-xylene, and then you keep it, lower the temperature, keep it around 70 degrees Celsius, 60 degrees, 80 degrees, 100 degrees Celsius. The polyethylene, right, makes a lamella. The length of polyethylene is more than a micron, right, 10 to the minus 6 meters. But independent of that length, they make a lamella of a thickness of 10 nanometers, right? It's more like a booklet or my tablet, right? And the lateral, this is a lateral dimension, this is a lateral. Lateral dimensions get bigger and bigger, but the thickness is only 10 nanometers. This is really amazing, right? Because you have very long chains. You would think they will all order like like in a pneumatic phase, or a well-organized pneumatic phase would be symmetric, right? Something like that, right? And we don't see that. Instead, they all make only 10 nanometer thick lamella. This is from solutions, right? I told you. But instead of this, suppose you take the polyethylene and melt, right? And then you quench it very quickly. They make these beautiful objects. They are called spherulites. And then they also stack like lamella. There's a stack of lots of lamellae. And the thickness of this lamella is 10 nanometers again. So there's a bunch of lamellae, but they are emanating like a three-dimensional structure. They make a thin lamellae. And then there are lots of other beautiful properties of polyethylene, right? Polyethylene, when you see under cross-polar microscopy, you see patterns like this, right? And I'm not going to go into details. Whenever you see patterns like this, it means that the molecules which are inside the system, or in general, the system has chirality. That means there are going to be left-handedness versus right-handedness, right? Polyethylene, as you know, does not have any optical center. There is no chirality here. The molecules are achiral, but nevertheless, they are able to organize. The spherulite is able to organize in this fashion. These are all in a textbook situation, textbook materials. You can read any book, you will see this. But the discovery was made in 1938, right? There is a single author paper in JACS. And this gentleman working in a DuPont made measurements, electron diffraction, and he came to the following conclusion. The macromolecules are folded back and forth upon themselves. So this is a very profound statement. He said the only way you can have a lamella of this type is only if the chains would fold back and forth. Folds like this, fold like that, like that, like that. The only way it can happen. Otherwise, you will not be able to have, this is the 10 nanometers, and the contour length is a 10 to the 3 nanometers, or more than 10 to the 3 nanometers. Okay, the length of the polymer is 3-4 orders of magnitude larger than the thickness into which the chain folds into. Okay. This is a key question, right? This is in 1938, right? But still, our community, polymer community, is trying to understand the fundamental principles behind this such an organization, how they are going to be organized in a spheritic fashion at a higher concentrations, etc. So there are lots of questions that should come to our minds, right? The questions are, for example, what is the melting temperature? Equilibrium melting temperature. What is equilibrium melting temperature, right? And what is the lamella thickness? We say lamella thickness is 10 nanometers. How do we understand it? How do we make a prediction? And how do these grow? And how do they melt? And what is the extent of ordering? What is the degree of crystallinity? And as I pointed out before, what is the role of external forces like a flow field, right? And the pressure and things like that. These are the kind of questions we have to understand and address and understand. In the interest of time, since we have only 2 more lectures left for this course, I will not go into all of them. We don't have time to go all of them. And also for an elementary course like this, these are getting to be challenging to understand. Even the community does not have a proper understanding of this. And this is one of the major challenging problems in polymer physics or in general polymer science, right? And I hope you folks will be able to get into some of these aspects and make discoveries. Right? So what I'm going to do is I'm going to go to a very simple description of some of the issues. Right? Basically, I'll focus on what's the melting temperature? How do we define it? What is lamella thickness? What are the simple methodologies we can go think about? And then we'll talk about growth kinetics. How do we describe the growth? And that's where I'm going to stop for this particular chapter. And these things are left as homework problems for you. Please go to the various books. There are lots of books. All books are struggling to understand because we don't understand it, because this is a kind of left as a future challenge for all of us. Okay. Given that, let me go back to what I was writing. All right. So what I'm going to do is, let me first define a melting temperature. How do we define melting temperature? Right. In principle, going back to the first picture, the melting temperature is at which the free energy of the liquid phase is same as the free energy of the solid phase, right? Crystalline phase. That's the definition, thermodynamic definition. And in a melt, one component system, free energy per molecule is a chemical potential. So I'm going to figure out what this TM0 is. Let's do a very simple calculation. For the details, you can look up the handout. So the question now is equilibrium melting temperature. I give the symbol TM0. Okay. So let me write down the chemical potential of the liquid phase. This is chemical potential per unit, repeat unit, chemical potential of a repeat unit, right, namely monomer in this case. Monomer as a part of the polymer. But this is in the liquid phase. Liquid phase. This is equal to, again, going back here, E minus Ts, but I'm going to be very general. Instead of writing E, I'm going to write H, which is enthalpy. So I write H in the liquid phase, that's the liquid phase, minus temperature times entropy in the liquid phase. I put little s, little h because you repeat unit. Not the capital S is for the whole system, whole organization. Here per monomer. That's why I'm using lowercase h and lowercase s. Now in the crystalline phase or a solid phase, chemical potential of a repeat unit, but in the crystalline phase C, that's equal to, again, enthalpy in the crystalline phase minus same temperature, some temperature, yes, C. These are the chemical potentials. So at the equilibrium melting temperature, at equilibrium melting temperature, they have to be the same, right? This has to be the same as this. That is, right? Because that's what we said. That's the definition of your melting temperature. They have to be the same. So how do you do that? At that, I equate this and this. So I have HL minus TM 0 SL, okay, that's equal to, I have this term, HC minus TM 0 SC. Okay. So from this, we can calculate TM0 because this is an equality. So I bring, right, I bring TM0 towards the right if you can, in that particular case. Right. So if you do this, you get an important expression. Do that TM0 is equal to solve this equation. Okay. If you do this, you'll have HL minus HC divided by right, solving this equation, right? Oops, I take HL to the, I take TM0 to the right hand side, and then if you solve this, you get this equation. So this is, I'm going to rewrite to be delta H divided by delta S. Okay? Delta S, sorry. I didn't want to write a big letter, delta S. So this is called, right, delta H is called heat of fusion. Heat of fusion. And then of course, delta S is entropy of fusion. Entropy of fusion. Okay, so this is actually a design principle. So always a TM0 is given by this ratio. So this gives you a good handle on how to control your melting temperature, equilibrium melting temperature. Because all that you have to do is intuitively, you play with this ratio, right? Suppose there is a very strong interaction, the difference in energy is going to be very big between, right, between liquid phase and crystalline phase. You know what delta H is, therefore that will give you what TM0 is. And also, as I'm repeating myself, the entropy is extremely important, right? Conformation entropy is important. So now let's look at, for example, suppose I have flow. If I have a flow and already the chains are stretched out, therefore the difference in entropy between the stretched out liquid phase and stretched out the crystalline phase is going to be very small. If that's the case, since it is a delta S, that's a difference that's going to be small, the equilibrium melting temperature will go up. That means they will crystallize very quickly, very, very easily at a higher temperature. Melting temperature is very high, right? So that's how we play to tune, industrially, we tune melting temperature based upon this very simple expression. Now, let me look at I want to define a very important quantity, which is driving force of crystallization. What is the driving force? Driving force of crystallization, when you say crystallization, obviously T is less than TM0. I'm looking at that temperature. Going back here, so in order to have crystallization, T is less than TM0. So under those conditions, what is the driving force? The driving force is delta mu, change in chemical potential, right? Which is given to be what I wrote down before, mu U0 minus mu UC. That's the driving force, right? Because now the stable phase is crystalline phase. So I define the driving force. If the driving force is higher, we'll look at the consequences. If the higher, when the chemical potential difference is less, if the driving force is less, we'll look at the consequences. But this is the key quantity that is going to be dictating our description of polymer crystallization. This is very easy to do because this is equal to, given me here, right? I have this and minus this one. So HL minus HC would be delta H. I have defined delta H is here, HL minus HC. I have gotten that. That's the first term. Then minus temperature, that's the crystallization temperature, SL minus SH, SL minus SH, that is a delta S. But I know what delta S by delta H is. So this is equal to delta H 1 minus T delta S by delta H. All right? Delta H times 1 is that. Delta H times this one gives me minus T delta S. Now, delta S by delta H here, delta S by delta H is 1 over Tm0. So this is equal to delta H 1 minus T divided by Tm0. So this I could rewrite to be delta H times delta T divided by Tm0. Well, delta T is our driving force. Delta T is equal to, as we write down, Tm0 minus T. So that is our driving force. So how much you quench? We know we are going to have crystal when the temperature is less than Tm0. The driving force is the distance of the temperature away from equilibrium melting temperature. So that is the driving force. So from now on, when we talk about driving force for crystallization, we can write in terms of delta mu or equivalently in terms of delta T, right? And I think I should stop here and we'll talk about other attributes of this phenomenon, okay? Okay, so as I pointed out, the driving force is a delta mu. And since the temperature is below the equilibrium melting temperature, right, I would write delta mu to be a positive number because that's good to work with. And that delta mu is written in terms of the experimental quantity, namely the quench depth, right? The equilibrium melting temperature minus temperature at which you are going to make the crystal, right? So if you know delta H and if you know Tm0, then we know the driving force. Delta H is easy to measure because this is per repeat unit. There are ways of figuring out what the heat of fusion is in terms of calorimetry, etc. And to date, we do not know precisely what the equilibrium melting temperature is for almost any polymer. So what we do is we extrapolate what Tm0 is. I'm going to show you an example of how we are going to extrapolate that. We extrapolate that, and then I will be able to put those numbers into this expression for delta mu. And every theory we develop to understand polymer crystallization, right, will have delta mu. Therefore, we can connect between the theory and experiment by using this formula. Because experimentally, we know what delta T is. Experimentally, you don't measure chemical potential, right? You measure only delta T. Right? So therefore, it is extremely important to know what the equilibrium melting temperature is. It's extremely important to figure out precisely what the equilibrium melting temperature is for the sample that we are talking about. In small molecular cases, it's very easy to determine, right, the temperature at which the small molecular system makes a crystal, right, which is a freezing point, or the temperature at which it melts, which is called the melting point. The freezing point and melting point are the same for small molecular cases. But that is not the situation with polymers. The melting temperature of the polymer is something, and when you crystallize it, they'll crystallize at any time. The crystallization temperature is different. They'll make some crystals as long as it's lower than a certain number. Okay, so this is an important thing. So please remember, our goal is to figure out what Tm0 is. We need to know that. That's an important quantity, all right? Otherwise, we will not be able to implement theoretical formulations to interpret the experimental data. And I want to emphasize that the experimental world and the theory world are not different. They should not be different. They should be coexisting. Theory and experiments, they should go together. Only then we make an understanding. So it is not good enough to say, oh, I do only experiments, or I do only theory. No, we have to do both, or we need to associate ourselves with good friends, good colleagues, where we can work together and understand both the theory and experiments to figure out how Mother Nature reveals her secrets. Okay. Now, towards this goal of TM0, I'm going to introduce a very important concept, which is actually due to Gibbs, Willard Gibbs, one of the founders of thermodynamics. And to do that, I'm going to take the example of lamella. So I want to know, suppose I have a lamella like this. Okay. Let's say the thickness of this lamella is L. That's my thickness of lamella. Then I have an area at the top. I told you from Stokes measurements as well as other people's spherulites, everything, the lamellar star. So I want to look at the lamella. In here, I have the chains going like this. And then let's take an ideal situation of a lamella like this. And this dimension, say, let's call L1, and this dimension is L2. So let me take L1 time is much greater than L, which we know because the lateral dimensions are microns, whereas this is only 10 nanometers. Similarly, L2 is much larger than, yeah, L is L3, right? And then I also say the area here, this is area, some area here. Surface area, fold surface area. Okay. Now let's write down the free energy of this lamella. The free energy of this lamella, right, which I'm going to write, say, I'm going to write in my following my lecture notes, I'm going to write this with delta G. So this is change free energy in making this crystal from the liquid state. And clearly, when they organize like this, there are interaction energies and accompanying entropy. I'm going to write this to be negative because it's a gain in free energy. Otherwise, it will not make the crystal, right? Volume is A, right, times L. This is area times length, this height. That gives me the volume of this lamella. And then the gain in free energy, right, that delta G is given in terms of delta mu, because that is the chemical potential difference. Since I define delta mu in this way, it's a positive quantity. I define that way. There's a positive quantity because this is positive. If this is positive, then delta mu is positive. Delta H is positive, that Tm0 is positive, right? So that's the reason why I have negative sign in here, because of my choice of convention for delta mu. Then what I have to do is, whenever you make a surface, there's a penalty. Create a wall, costs free energy. And that can come from both entropy and energy. So this is going to be plus, right? There's an area here, area, and let me call the surface tension or the interfacial free energy per unit area is sigma F. This F is for representing fold surface. That means the chain is folding back and forth, right? Here is a fold, there's another fold, another fold. That's the reason I put this subscript fold F. Sigma is a surface free energy. A is surface area. So the surface area times surface tension per unit area gives me the free energy corresponding to the surface. But there are two surfaces. There is one at the top. Similarly, the same surface area is at the bottom of this lamella. Therefore, I put a factor of 2 here. Okay. Now the question is, what is the melting temperature of this lamella? Given this picture, right? What is melting temperature of, right, this lamella? At this point, I can wonder, oh, there are also other surfaces. There is one lateral surface here, another lateral surface here, and then the back, and then another one here. There are 4 lateral surfaces. So there should be 4 times, 4 times this surface area, right, times, the 4 surface free energy. For the time being, I'm going to ignore that for a very good reason. It turns out it is not that important. It will turn out to be not important if you do the calculations. Okay, I'm going to, because as you'll see, right, the L1 times L2 times L2 is the area. If I take this one, it will be L2 times this length. Now, since this is the L1 times L2 is a product, right, which is the area, here I have this only square root of A, square root of area, because if they are the same, square root of A times L, which is going to be negligible. Square root of A times L is negligible in comparison with A. Therefore, that's not that important. All right. Now let's try to predict melting temperature out of this. because remember melting temperature is delta G is 0. Again, going back to this picture, melting temperature is at which these free energies are the same. Delta G is 0 at the melting temperature. Now let's do this, because I know I have an expression for delta mu. We just derived it. Delta mu is equal to delta H times delta T by Tm0. We know that. So this is equal to negative AL delta H 1 minus T by Tm0. Okay. Plus 2A sigma F. At Tm. Okay, this is the melting temperature of the lamella. Tm0 is a full ordering of the whole system. Okay, here, this lamella is going to melt at lamella of thickness L. Okay, this is the melting. At that temperature, delta G is 0. At this temperature, delta Z is equal to 0. Therefore, what I get is, let's do this, right? Okay, so A, L, delta H times 1 minus T by Tm by Tm0 is equal to 2A sigma F. Okay, A times L delta H is equal to this. Right. So this factor A, they get canceled out. This A goes away with that A. Okay. Therefore, now let's solve this equation to make sure we understand this properly, because this is an extremely important expression. This comes in almost all aspects of nanoscience. Whenever you have nano systems, the melting temperature or a corresponding property of that type depends upon the size of the object. Now, it is not the same temperature, melting temperature, as in the bulk. When you reduce a scale, there's a very unique relationship between the order-disorder transition with its size. So that's the reason I'm going through this, right? So I have 1 minus Tm by Tm0 is equal to 2 sigma F by delta H. Therefore, I can bring this one, right, to the left. If I do this, I get Tm is equal to Tm0. Let me write in a corner because I need some space. Tm is equal to Tm0 times 1 minus 2 sigma F. Oh, I made a mistake. There is an L here. Delta H L. Okay. So when you solve this, you bring this to the left-hand side, you have 1 minus 2 sigma F divided by L delta H. And then since I am here Tm by Tm0, multiply by Tm0. So this is called the Gibbs-Thomson equation. Gibbs-Thomson. And what does it say? If the lamellar thickness is infinity, suppose it makes a full crystal, 1 over infinity is 0, then the melting temperature is Tm0, equal melting temperature. When I make a lamellar thickness smaller and smaller, right, this becomes healthier and healthier with a negative sign, and the melting temperature of that lamella becomes smaller and smaller. So melting temperature of a thin lamella is lower than the melting temperature of a thicker lamella. So I can plot Tm versus 1 over L, right? If I plot a TM y-axis, the left-hand side versus 1 over L, look at this, 1 over L here. Because we know already the polymers don't make full crystalline state. We know that. So we are going to have lamella, for example, right? We know that we saw in experiments. So that means, right, I will not be able to go to L becoming contour length. I will not be able to make measurements under normal conditions to find out what the melting temperature is for full crystal because it doesn't form. But I can make measurements by depending upon the temperature where I make the crystal, then I'll measure the lamella thickness there. Then I can plot Tm versus 1 over L. So according to this Gibbs-Thomson equation, you get data like this, like that. That's what you get. Okay. Then you extrapolate. That gives you, this extrapolated value gives me Tm0. So this is what normally people use. Okay. This is how they get this Tm0. Right. They use a Gibbs-Thomson equation. That is, normally, experimentally, what you do is you take your polymer at melt or from solutions, lower the temperature, it makes a lamella. And depending upon the conditions, if it's a solution, the lamella is floating around. If it's in a melt, it's a spherulite. And you do X-ray diffraction, electron diffraction, etc., to figure out what the lamella thickness is. So at one temperature, you make the crystal. At that temperature, you measure lamella thickness. Then you repeat the experiment again and again at the different temperatures, and you measure the lamella thicknesses corresponding to them. Then you plot temperature where you crystallized with the 1 over L, or you melt it for a lower, some lamella that you make. Right after you make the lamella, you melt it and find what the melting temperature is. And then when you extrapolate it for infinitely long lamella thickness, then you get Tm0. Right. This is the normal practice. Now, before I go further, I will not go into details, but I want to emphasize this once more. So this is how you get melting temperature as a function of thickness of the lamella. Now, but on the other hand, if you go and look at the real world, this is 1 over L, this is temperature, and then what normally people would say is this is my Tm0, and then that is extrapolated. This is extrapolated from these data points. These are data, and this is extrapolated. So this is called a melting curve. Melting line. And it turns out there are many situations where this is not true. This is not true means you cannot make crystals beyond this point. There is, what happens is data actually stops somewhere here. And this corresponds to 0 growth rate. In other words, crystals don't grow at temperatures beyond that. At temperatures above this, right, they don't grow. But these are facts. These are experimental facts. And then there had been many suggestions in the literature. One is from Strobel, and it's very well written in his book. Right? He says there are interlude of liquid crystal like a mesomorphic state. That turns out to be somewhere here. That's what he believes. That is trouble. Even today, I think that's the context. And now people now are recognizing, particularly coming from my own laboratory, we believe that's more like a metastable state. So I'll use a different color. We think this is a metastable state. Why is that? Okay. The reason is simple. I told you there is always, even though I make a crystal here, there is always a chance that it's going to make some fluctuations. There will be some liquid state. For polymer case, that liquid state has lots of heterogeneity, right? Which in turn leads to what we call memory effect. Right? But in general, that is possible due to fluctuations. But except here, the fluctuations are highly correlated. Then another argument is this is my argument, is the equilibrium lamella thickness let me call L star, or I can even call L equilibrium. L equilibrium is not L going to infinity, right? That's what people argue, right? So we argued with this. So in fact, this is 1 over L equilibrium. Everything stops there. L equilibrium is precisely the point where you have zero growth rate. So therefore, the system, the crystallization temperature is not that one. It's not Tm0. Instead, it is this one. This is Tm corresponding to equilibrium, not the extrapolated value. And please notice, this is a modern, today's literature, right? I mean, the textbooks don't talk about it, right? So this is what, since you are a new generation of scholars, you need to pick with what is correct instead of going back to ancient views. So please remember, the key quantity, which is the driving force for crystallization, right, is this one. Delta T is equal to Tm0 minus T. So we need to know what that Tm0 is. Without knowing that, we will be getting wrong physics or wrong predictions. Therefore, there is a huge difference between whether you choose this as your equilibrium melting temperature or this extrapolated value. Okay? This difference could be easily 5 degrees. And 5 degrees is a huge number, as you are going to see. When delta T quantity that changes by 5 degrees, the whole kinetics of polymer crystallization would be entirely different. Okay, so this is a very important summary of current or a commentary on the current situation in terms of equilibrium melting temperature. Okay, so here we talked about Gibbs-Thompson law in terms of how to use this, and then how we talk about the role of finite lamellar thickness on melting temperature, and then how does this happen? This happens because of this entropic term. Okay, this is responsible. This is responsible for this behavior. Okay, now I think we are, instead of going into too much details, let's talk about kinetics of growth, right? Once you make this lamella, for example, how does it grow? And we have talked about this in the introduction of this already before, right? Again, let me remind you, right? So what we are trying to do is we start from a state here, the liquid state, and then quench it, and then make the crystal. And in this process, there's going to be a barrier, right? So how do we do this? Let's go and look at, for example, the free energy of the birth of nucleus. Okay, so now I'm going to talk about growth kinetics. Whenever it has to pass through a barrier, it has to be nucleation growth. remember we talked about this, the two different mechanisms, right? When you have a state which is metastable, not unstable, metastable, then how does it become stable? So when I have the liquid state here, right, I am in a metastable state. As soon as I take this system, quench the temperature, the starting point is here, and that now becomes this one. I was there, suddenly I quenched it becomes a metastable state. So the way that's going to evolve with the time to go into the the free energy, globally stable state is by crossing a barrier. And that's a nucleation mechanism. And I don't have to go through this. Please go back and look at your earlier notes. Suppose I have a spherical nucleus. This is a summary. A spherical nucleus. That means I have a spherical particle of radius r, spherical nucleus of radius r. Okay, maybe I'll use a small r. And what is the free energy of making this sphere? And that's equal to volume is 4 by 3 pi r cubed, and delta mu again. Now you know what delta mu is. I gave the definition. Plus surface area 4 pi r square times sigma. I do not have to distinguish between fold surface and lateral surface because it's spherical nucleus, right? That's the formula. And from there, we already talked about it. Delta mu is equal to delta H, right? And then I have delta T by Tm0, for example, right? You know that. And then as you discussed before, if I plot this delta G versus R, there is a barrier, right? It goes for small values of R, it goes like R square, and then goes up like this and comes down like this. And here is critical nucleus RC. And then we worked on all these things. Please go back and look at it. This critical value of RC is, I'm copying from my notes, 2 sigma Tm0 divided by delta H delta T. So the radius, critical nucleus size is 1 over delta T. Similarly, the barrier, this is a barrier. I'm recapitulating what we did in the previous lecture. And that goes like some numbers I have given you, 16 pi over 3 sigma cubed Tm0 squared divided by delta H squared and delta T squared. And I want to emphasize that in three-dimensional nucleation like this, when delta T is small, right, the barrier goes big. The barrier goes big, the system will struggle to make the globally free energy minimum state because delta G has to be negative at the end. It has to be R becomes large, so the barrier will be too high. Now let's try to do the same problem for a lamellar thickness. So this goes like 1 over delta T square, right? And then therefore the nucleation rate is going to be very low, etc. Let's repeat this calculation which we did before for the lamella, right? Let me take a lamella of a general type. Right, let me see, remember we are talking about a lamella of this type, right? Right, that's a cylindrical kind of thing, right? So let's write the free energy of this. Delta G is equal to, right? Let me call this tablet to be of radius R, and let me call this length to be L, right? Instead of taking a square tablet, I'm taking a cylindrical or disc-like tablet. You could do the same calculation for at the top being square or a rectangle, right? To make my argument clear, I don't want to have L1, L2, etc. I simply have R to be radius. Therefore, delta G is negative. Volume is what? Pi R squared, that's surface area times the length, that's the volume. Then I have delta mu. The way I had before, right? In Gibbs-Thompson law, that's what I did. A, L, delta H, something like this, right? Now here, the calculation is done for already made lamella. I made the lamella already, large lamella, and then I calculated the melting temperature of that lamella. But here, I do not know yet whether I made this big lamella. I'm interested in nucleating that formation of that lamella, right? So for that, I do not know, or I cannot take the assumption that the area is so large, right? I do not know what it is. I'm trying to figure out what that R is, right? What L is. So minus pi R square L delta mu, and then I have, look at this is a fold. Let's see, sorry. This is a fold surface. This is a lateral surface. Okay. So let me look at the lateral surface. The lateral surface area would be the perimeter of this top circle times L. Okay. 2 pi R times L. That's the area of this lateral surface times sigma L. This is lateral surface free energy. And then the fold surface free energy. That you know that, right? The fold surface free energy is a pi R squared, the surface area. There are two surfaces and sigma F. This is a fold surface free energy. Okay. Then what we do is we minimize this. Okay. You do exactly what we did before. You know, construct the free energy delta G as a function of R. Now it's a two-dimensional minimization because I do not know L, I do not know R, right? So if you do that, if you work it out, what happens is the free energy barrier turns out to be something like this. This is equal to, you work it out, 8 pi sigma sigma L square, and then Tm0 square divided by, it's all in the handout, it's derived there, okay? So I don't want to go through long derivation here because you can go and look at the notes and work them out. But the important thing to realize is this goes like 1 over delta T square. That's the important thing. Okay? Now, if you know this F star, that is the nucleation barrier, you also know the nucleation rate. The nucleation rate is equal to, let me write this to be J. We had this formula before. You can go back and look at it, right? And I'm not going to write the prefactors. There are some prefactors in here, right? The important thing to recognize is this goes like e to the minus F star over KT. This is the important fact. And in terms of temperature, this goes like e to the minus, okay, 1 over, because free energy star, F star is 1 over delta T squared with all these quantities, right? So I'm going to write that to be some number divided by temperature, because kBT at the temperature, and F star goes like 1 over delta T squared, and that's the way it appears. Okay, this is for three-dimensional nucleation. Since this nucleation is taking place on its own, right, without any surfaces, without any catalyst around, without any other external fields, this is three-dimensional homogeneous nucleation. In a polymer field, we call this to be primary nucleation. Okay. Okay. So this is what we did. Right. This is what we did means we did this. Right. We did this calculation before, and you can use the same idea going back almost a month ago. Same idea, and then you write the free energy expression for this tablet, and then you minimize the free energy based upon this. You can go and look at, right, what the critical value is. Now, instead of only one radius here, we have the capital R, radius of the disk, right, versus, and also the lamellar thickness. Yeah, there are two variables, you minimize them. Suppose you want to make more interesting, your calculation more interesting. Suppose I want to have a parallel pipette. I have, in one dimension, I have L1, another dimension is the L2, and the third dimension is the L. And then construct this and minimize this with respect to those three variables. And then you will be able to get F star. Apart from these prefactors, still it will go like 1 over delta T square. The prefactor will change the geometry. They depend on the geometry. And then the punchline is this. Now, please contrast this situation with a different situation which we are going to talk about in the next lecture. Suppose I have two-dimensional. Suppose I have, say for example, I have a surface like this. I already made a crystal, okay, some lamella because of the homogeneous nucleation. Suppose I did this. I have this. Now, what I'm going to do is I'm going to have growth in 2 dimensions. Instead of writing in 3 dimensions, right? Let's assume I have growth here. This is a 2-dimensional plane, right? This is a 2-dimensional plane. Suppose I have some growth like this. A 2-dimensional nucleus. All right, 1-dimensional nucleus would be more like fibers. Okay. So this is, suppose I have some proteins like in polypeptides or so, and they are organizing like in 1-dimensional chain, like amyloids, for example, right? That's in 1-dimensional growth. But this is 2-dimensional. And the one that I talked about here is a 3-dimensional. This is a 3-dimensional homogeneous nucleation. This is going to be 2-dimensional. And that's very easy to do because we did the homework problem, right? Because for this particular case, delta G goes like negative, and some number, let's not worry about it, right? Volume is, let's say R square, right? So volume, that's a 2-dimensional disk, for example, 2-dimensional R square, essentially R square times delta mu, right? And then the surface tension would be perimeter of this times, right, plus perimeter will go like a R, and then I have sigma corresponding to the interfacial tension, line tension, if you like. Then you can work out, right? You can work out the barrier for this, okay? Then if you want, we can do this. If you work it out, well, let's do this. Work it out, it will be 1 over delta T. Please go back and refer to our earlier notes. So this is for 2-dimensional crystallization, 2-dimensional nucleation, sorry, 2-dimensional. Okay, time is up. Homogeneous nucleation. So based on the arguments we had already, the nucleation rate, therefore, nucleation rate turns out to be, for this problem, for 2-dimensional homogeneous nucleation rate goes like e to the minus f star over kt, and then putting this f star in here, e to the minus some number divided by t times delta t. What did I write? Yeah, t times delta t. please notice this, right? Here, if it's two-dimensional homogeneous nucleation, that's what it is, if it's alone. But now, if this is taking place on the surface of a lamella, which is already formed by primary nucleation, then now this is secondary nucleation. Okay, I have to prove this because we are expecting already, intuitively we are expecting, because in two-dimensional nucleation growth, homogeneous nucleation rate goes like e to the minus 1 over temperature times quench depth, which is qualitatively different from what we have in here, 1 over temperature times delta T squared. But now, if this process were to happen on the surface of a lamella, lateral surface, then I expect the same phenomenon without doing too much details, right? Without considering too much. Intuitively, that's what I would expect. Of course, the details will come into play in terms of this number. What is that? How does it depend upon various features of this? And that is the subject of the next lecture. Okay, so I'm going to stop here.